Hello everyone, my name is Morgan Zhang from Moldex3D EMEA team. Today, I'm going to introduce how to optimize gate location to improve mobility. So what is the gate design? The gate is the link between the cavity and the rounder. And we usually care about few things, such as the gate size, the shape, gate locations, and gate numbers. And if possible, we will always pursue the automatic gate in order to decrease the labor cost. And for the design of the gate, there are some factors summarized here briefly. We will say the type of the gate, size, and location greatly affect our product. And generally speaking, the gate should be small and easy to digate. It should not cause any mark on the surface of the cavity. And we usually care about the molding defect, such as the wear line, because we don't want to let the wear line appear at some specific region. So instead, we will just change the gate location to shift the wear line to the less critical area. Okay. Other defects such as like the jetting or the show shot, etc., should be avoided during the production. The cost of the tooling is also a consideration because we don't want to increase our cost to use too much gate. So the suitable gate number is a common critical issue. Okay. For the part design, it's always suggested that the wall thickness should be uniform. But sometimes it's very hard to achieve, especially for some of the big and complicated geometry, such as the car bumper or the dashboard. So instead, we will suggest to put the gate on the thicker thickness area in order to get the better packing effect so that the product quality will be better. And for the material, since the different material had the different flowability, it's important to make sure that the gate number is enough in order to prevent the show shot or the hesitation. And if the material contains fiber, we also care about the gate precision because the gate precision will greatly affect the fiber orientation so that the structural strength will be changed. Okay. For the type of the gate, we can divide two categories. One is the manually trimmed gate. Another one is the automatically trimmed gate. And each type of the gate provides different functionalities. and since there are many considerations, for example, for the exterior cavity or exterior part, we don't want to put the gate on the outer surface. So in this situation, we will use the tunnel gate with the ejector pin, or we can call it jump gate, and put it into the interior surface. So then we can just maintain the good quality of the outer surface. Other example like the packing pressure. With the bigger size of the gate, we will get the better packing effect so that the product quality will be better. But it will lead to another situation. For example, with the bigger size of the gate, it might be hard to digate. Since there are many considerations, so that's why there are many different types of the gate. But general, we will prefer to choose the automatic trim gate in order to decrease the labor cost. In Moldex3D, we provide a lot of different types of the gate, such as the cashew gate, fan gate, and pin gate. And if the customer has some special gate design or the special rounder design, we still can import the geometry into the Moldex3D to run the calculation. For the common molding issue, if we put the gate in the unsuitable gate position, we might have some potential problem, such as the show shot, wear line, air jetting, and so on. All these defects should be avoided during the production. And if the material contains fiber, we will always care about the fiber orientation because it will influence our structural strength. And we will say the gate position plays a very important role to influence the fiber orientation. So it's very important to find a suitable gate position. So how can we optimize the gate position? In the Moldex3D, we provide a lot of the simulation tool to help us to solve this problem. and I will just start to introduce that. Okay, so what we can do in the Moldex3D, the best strategy to decide the gate precision in a very short period of time. In Moldex3D, we provide the 5 useful tools, which are thickness, availability ratio, gate location advisor, quick flow, and the standard flow. And I will introduce them one by one in the next pages.
Okay, so the first one is the thickness. We usually will use this function to check the thickness distribution inside of the cavity. So like this case, we can just fix or change the color bar or just score the dotted bar to know more about the detailed information of the cavity. And also we can just score the color bar to know the average thickness distribution. And in this case, we can see that the thickness is around 3.3 millimeter in the most region.
Okay, so this is the first tip for the thickness. We will always suggest to put the gate on the thicker area in order to get the patting effect. So we can see like the below example. We put the gate in the 2 different locations. One is on the thicker thickness area. Another one is on the thin thickness area. So on the thicker thickness area, which is around 3 millimeter, and this one is only 1 millimeter. As a result, we can see that the pressure distribution is different. And if we see deeply, we can find that in this situation, the packing effect still very well in the middle of the cavity. So it means that we can get a better packing effect by that. If we look to another case, since the thinner area will be frozen earlier than the thick area, so it might be hard to transfer the pressure by this way. So that's why it would be hard to maintain the packing pressure in the middle of the cavity, or also the last fill region. With the lower packing pressure in the last fill region, it might lead to another defect, such as the void or the thin mar. Okay. And if we look into deeper, we can find that even we use the same process setting, the pressure range will be different. So still, we can find that using this way, the maximum packing pressure will be lower, but still we can get a better packing effect. So we can use this method to induce our sprue pressure. Okay. This is the tip for the thickness. Second tip for the thickness. As I mentioned above, in the tip number 1, we will suggest to put the gate in the thicker thickness area. But if we choose the sand area, we will suggest to put the gate in the thin thickness direction in order to avoid the jetting. So like the left picture, we can see that if we put the gate like this way, it might have some of the jetting phenomena. It might be happen for some of the high flowability material with the high injection pressure. So we always will put the gate like this way in the thin thickness direction. Okay, for the second tool, availability ratio, which means that the flow length divided by the thickness. And I would say this is a very useful tool to help us to determine the suitable gate number and the suitable gate precision. And it's very good for some of the complicated geometry and ununiform geometry, because for this model, it's very hard for us to decide the suitable gate number by our experience. So that's why we provide this tool to help us to evaluate. And we can also use that to get the fitting line pattern in a second. So as long as we put the gate on the cavity, then we can start to use this tool. As long as we put the value on the availability ratio, then it will show the black circle. It means that this is the current availability value. So we can score the bar to know about to check whether the value is within the suggested material range. For example, if we choose the ABS, we can find there's the minima and the maximum value. Why there's a difference? It's because even in the same type of the material, it still had the different flowability for the different material. So if we don't have any idea, or if we are not very familiar to the current using material, we will suggest to use the minimum value as our criteria, just in case to decide the suitable gate number and the suitable gate precision.
Okay. For the gate location divisor, if we don't have any idea to decide the suitable gate location, we could try to use this function to help us to get more clues. So for example, we can use this model and then tick on the gate location divisor. We can choose our desired gate number. And if we don't want to put the gate in the specific region, we can use this function. And also, if we would like to just put the gate in our desired surface, we can also use this function. For example, we can just select our desired surface. Okay, so as long as I choose the desired surface, then click apply, then the system will start to calculate the suitable gate precision based on the cavity and based on the cavity thickness, and then it will show the suitable gate precision in order to achieve the flow balance. Okay, so it will just show the suitable gate number, and then we can start combine using the velocity value to check the suitable flow distance. So we can just score the bar, and then the current velocity value will be changed. Okay. So like this case, we can see the maximum value might be more or less 20. And if we look detail about this table, we can see that the most all of this plastic uh, uh, we can see that the value is far below than each material's minimum value. So which means that it's not necessary to use the two gate design in this case. Instead, we can only use one gate to fill the whole cavity without any problem. So we can use this tool to help us to find the suitable gate number and the suitable gate precision.
Then for the for the quick flow, it's a very useful tool to help us to predict the wear line in a very short period of time. So it's especially good for some of the complicated and the big geometry, because usually for the big geometry, the total mesh count will be more, and if we have a lot of the design change and want to do the simulation, it might take a lot of time to do the interaction. So that's why we provide the quick flow to help us to speed up the interaction in a short period of time. So we can see that if we use the standard flow, in this car bumper case, it took us around 2.6 hours. But if we choose the quick flow, it only took us around 9 minutes. So it means that we can do many interactions in a very short period of time. But with the very good tool, but we still do some assumption and the limitation about this function. So for the assumption, for the material, which is the isothermal, and the temperature is the melt temperature, and for the limitation, we only provide the melt front type result and the wear line result. So it means that we can just use that to predict the suitable wear line precision. Okay. And it's good for the big geometry and the multiple gate design, not for the small part and the single gate design. It's because for the small part, the total mesh count is less. So it's not necessary to use the quick flow to run the simulation. It's okay to just use the standard flow directly. And in the quick flow, we only support the get only, not support the runner system, because we want to do the simplification, okay? And we cannot predict the show shot, and it's not include the fiber calculation. Okay, after we do the quick flow, since we do the many assumption about the quick flow, so we will always suggest to run the standard flow to do the final check, as long as we choose the suitable get design from the quick flow. Okay. Okay, so now I will start to introduce each situation when each situation. Okay. For the situation one, our customer is have the small part, and we already have the runner design. Since this is the very small part, so the total mesh count is less, and the total get number is less. So in this situation, it's not necessary to use the quick flow. So instead, we can start to use the standard flow directly to do the interaction. Okay. For the situation two, our customer is using the big geometry, such as like the car bumper or like the dashboard. So we probably know our desired get region, but not very sure exactly the get precision. Or maybe using we might using the hard roundabout gate control, but we would like to check the suitable get sequential time. Or maybe we have built the more, but the result is not very well. So we would like to do some of the partial modification. So like for the big geometry, since the total mesh count is more, and the total get number is more. And in this stage, we would like to just check the wheel line. And so we just provide the quick flow. So in this situation, we can do the iteration by using the quick flow. And as long as we choose the suitable get design, we can just use the standard flow as a final check. Okay. For the situation three, we only had the cavity design. So now we are looking for the suitable get number and the suitable get precision. So in this situation, we will suggest to combine using these three tools: thickness, availability ratio, get location advisor, to help us to find more clue to design the get. But still, we will always suggest to use the standard flow eventually for the last check. Okay. For the case study, we will talk about this company. Okay. Okay. In today's part, which is the car light part, since this is the exterior part, we always care about the wheel line, sigma, and the warpage. And in this case, it's okay to use the one get design to fill the whole cavity, but because the customer would like to achieve the flow balance, so let's use the two design. And for their current challenge, they found if they use the original get design, they will find there's an obvious wheel line appear on the exterior part. So they would like to just change the get position in order to shift the wheel line position. So for their challenge, their current situation, they certainly need to change the get location, but where is the good position? And under the day-night pressure, they don't have they are unable to repair the mold many times. So their goal is fix the wheel line and other appearance defect, and they don't want to do the more repairing many times because they don't want to waste the cost, and also they want to just meet the day-night. Okay. So this is the brief introduction of the product. This is the headlight reflector. The size, the length is around 200 millimeter. Wide is around 520 millimeter. The height is around 500 millimeter. And the average thickness is 2.5 millimeter. And they use the total mesh count is around 4.3 millions. Okay. So for their original design, we just use the standard flow to do the check. So as a result, we've actually found there's a wheel line appear in the corner, which is correspond to the reality. Okay, so let's start to decide to do the to change the gate position. So they maintain the gate number 1 and only move the gate number 2, and they have the 3 plane. The plane 1 is move the gate from the middle to the left 2 millimeter. Plane 2 is moved to the left 40 millimeter, and the plane 3 is moved from middle to the left corner. And since they already built the cable, built more, so the high system is fixed in this region. So if we change the gate design, the length of the core will be increased. Okay, so we can see that this length will be longer. So since this case, fixing the wear line is our first priority, and this is the kind of like normal and big geometry. The total mesh count is around 4.3 millions. And there are many gate location design we would like to check. So in this situation, it's very suitable to use the situation tool, which is use the quick flow to do the interaction and then to run the standard flow as a final check. Okay. So we just use the quick flow to validate the gate design. So we found the plane 1, the wear line didn't change a lot. Okay. And for the plane 2, the wear line appear on the corner, and the customer said the appearance looked quite okay. And for the plane 3, the appearance looked okay as well, but the runner is too long because the high runner is fixed here, so the core runner is too long, so the cost will also increase. So based above, the customer just choose the plane 2 as their final solution. So they actually do the more trial based on the plane 2, and as a result, they just get a very good. They just shift the wheel line, so it's not appear on the original position. And actually, they only do one more. They only repair more only one time, so they are very satisfied with this current result. Okay. So this is the comparison between the standard flow and the quick flow. In this situation, if we use the standard flow, it takes us around 3.6 hours. But if we use the quick flow, it only took us 20 minutes. So if we choose the situation 2, it can help us to set a lot of time. For example, if we use the traditional method, just use the standard flow for the all simulation, the total time is around 40 hours. But if you use the situation 2, it can help us to save more than 6 hours. So it means that it can help us to save the 45% of the time. And we only just test the 3 design. But if we use the more design change, the difference will be more obviously. Okay. So here's today's conclusion. In Moldex3D, we provide the 5 useful tools to help us to optimize the gate location, which are thickness, adaptability ratio, gate location advisor, quick flow, and the standard flow. And we can combine using these 5 tools to help us to decide the suitable gate position and the suitable gate number. Okay. And using quick flow can help us to predict the wheel line in a very short period of time. So it's also always recommend to use for the big geometry, such as like the big car bumper or the dashboard. Finally, it's always suggest to run the standard flow to do the final check, as long as we choose the good design, good gate design from the quick flow.